So the beginning of today's lecture will be an example presented by my PhD student Xinzhou. So he is going to show you a concrete application about which you can apply either a multinomial regression or a negative binomial regression. So for the multinomial regression, you can consider it to be a generalization of the binomial logistic regression we talk about for group data logistic regression. And here he has more than 2 groups. And so each observation in the response will be a count vector. Let's say if you have 3 categories, then you'll have 3 counts as the response of observation 1, observation 2, and so on. So that will be the data format. So I'll let Xinzhou begin so that you can see this example and understand the differences between the 2 approaches.
Okay, thank you, Jessica, for inviting me. So today I'd like to introduce an example of regression models for count data. And in fact, I will compare 2 models here, the multinomial logistic regression and the negative binomial regression. In fact, this example is motivated by my research project, and in this data we have a biological data set which has multiple groups. But here, for convenience, I would like to introduce. So here, the problem becomes the problem about children's food choice. So as we know, children's food choice is influenced by different factors, including the age, gender, family income of these children. And different food choices can be categorized. For example, we can categorize the food into fast food, healthy choices, vegan, or actually we just didn't have food. So if we summarize the food choices of the children in a month, for example, 30 days, then we can have the following data set. So each row will be a child, each column will be a covariate. So for example, the age, gender, and income of these children. And then we can also summarize the food choice of the children in a month as the last 4 columns of the data set. For example, for the first children, within a month, he or she has 10 fast food, 10 healthy food, and 10 vegan. So this is the summarized table of the food choices for the children. And if we want to study the relationship between these factors and the food choices, we have 2 ways to do this. The first way to do this is to use the negative binomial regression. So for negative binomial regression, we look at 1 category at a time. So for example, the fast food category at first. So we will study the relationship between these covariates and this 1 response. For negative binomial regression, this regression is models the count data. So the response can only be count data. And the model for this regression is as follows. So first, we assume that for each child I, the count yi follows negative binomial regression with mean mu I and a dispersion parameter alpha. So here alpha is something called dispersion parameter. So for negative binomial distribution, its variance is larger than its mean, and the dispersion is is something describes the relationship between the variance and the mean. So this is the distribution of the counts, and we model the mean of the counts as this. So we can see that it is a exponential of linear expression of the linear combination of the of the covariance.
And so, Xinzhou, just to make a side note, I think because here, when you look at one category at a time, I just realized that the total is 30 days, right? So each category, each count in each category cannot be greater than 30.
Oh, yes, it cannot be greater than
Greater
30.
than 30. So in this case, probably it's more reasonable to use the binomial logistic regression model, right?
Yes, you're right.
Yeah, but that's just pretend that you don't have this information.
Yeah.
So the counts can be as large as infinity. Just
Yes.
pretend that. Yeah. And also there's a slight difference I want to point out in Xinzhou's notation for the systematic structure here from what we have in the class. So in our class, when we say beta is p-dimensional, we included the intercept. But Xinzhou here left out the intercept as a separate thing. So he has actually p+1 coefficients in his setting. Yeah.
Okay.
Okay, please continue.
Okay, then after finish the first category, and then we can go to the next category. So the conclusion we can get from the negative binomial regression is that whether, for example, age is related to the choice of fast food, or whether gender is related to the choice of healthy food. So we can only make conclusions for one specific category. So this is a limitation of the negative binomial regression. And then another way to do this is the multinomial logistic regression. So for this regression, we can look at all the categories at the same time. So for example, the predictor are still the covariance, but the response can be all the category information. And here, as Jessica has said, it is similar to the binomial logistic regression in that it also focuses on the proportion of each category. But here we have more than two categories. So for example, if I think maybe you are familiar with this formula, it is similar to the logit function in logistic regression. So here, as we have more than two categories, we will have more such functions. For example, we can model the proportion for vegan and the proportion for fast food using this formula. It is still similar to the logit function, and then we can, and for healthy food, we can also have such a function, but we have probability that each child I choose healthy food as food choice, that probability over the probability that for choosing the fast food. And we can also have such a formula for none, for not having food. And this is so as we have four categories, we have three such formulas, and then we can calculate the probability that this child choose fast food and this child choose healthy food, choose vegan, or choose none. And then this whole vector for child I, so this line will be the observed value of yi, and the yi will follow a multinomial distribution, which all four values sum up to 30, and each value have the following probability. So this will be the random structure for the multinomial logistic regression. So from this, we can see that the multinomial logistic regression look at all the categories at the same time. So so we can draw conclusions like the age or gender is associated with the food choice. And we can, for example, calculate the p-value for each covariate by doing doing a likelihood ratio test or word test. So this is an advantage of the multinomial logistic regression. It can look at all the categories at the same time and make a more general conclusion. So that's the difference between these two models. And if you want to implement these models in R, so here are the packages and functions for these models. For negative binomial regression, so we can use the grm.nb function in the MASS library package, and this is the formula for the negative binomial regression. And if you want to use the multinomial logistic regression, you can use the package called nnet, and here we can just make we can summarize all the columns that are the categories that we are interested in, and use a multi-norm function to do the regression with category as the response. So I think that's all for for my part. And do you have any questions?
Yeah, so I just want to add to Xinzhou's point that these two types of regression, in fact, answer different questions.
Yeah.
So the negative binomial regression answers the question similar as the Poisson regression do. That is, whether the expected count of response I is whether the expectation of response I changes with a covariate. That's the first question. And the second question is, does the overall proportion of response I, the expected proportions of response I, change with one covariate? So that's why for different types of questions you want to investigate, you will use different types of regression.
Yes.
And you see that in those two cases, both the random structure and the systematic structure are different. Okay, so do we have questions before we finish this part? Thank you very much, Xinzhou.
You're welcome.
Okay, so if there's no more question, so we'll just resume our regular lecture and move to the third part of our lecture, which is the linear mixed effect models, also known as the hierarchical linear models. Okay, so I'm going to share my screen. So I would first introduce the motivation for doing this linear mixed effect models. So this is short as LMM, or it can be written as hierarchical linear models, short as HLM. They are essentially the same thing, except that when we write LMM, we just write down the model in one layer. But when we write it as a hierarchical model, the model has two layers. We can see that later. And also, in essence, I can tell you that they are related to a very interesting concept called empirical base, which lies between frequentist and Bayesian. So what does this mean is that in the empirical base, you assume a parameter follows a distribution. And this distribution in the Bayesian sense is what we call the prior. But if you're a true Bayesian, then a true prior must have its parameters being known, right? So you know the prior, that's your knowledge. And so you know the distribution already. You use the parameter following this distribution combined with your data following distribution specified by this parameter, that's something that will give us the likelihood. You combine the likelihood with the prior to give you the posterior. That will be the distribution of the parameter given your data. And from that posterior, you will talk about that parameter. That's a typical Bayesian inference. So let me write it down. So what I mean is that, let's say, I'll just use linear model as an example, okay, to start with. Bayesian linear model. And then I'll come back to what we mean by empirical base. So in Bayesian linear model, the first layer or the bottom layer we have is this. Yi follows or independently follows normal distribution with mean as xi transpose beta. That's the mean. And the variance sigma square. That's what we have in our random structure, if you recall. But we were frequently unknown but fixed, so we want to estimate it. Under the Bayesian linear model, then you will assume this beta, which is p-dimensional, itself would follow a p-dimensional normal distribution. So this is a multivariate normal distribution with its own mean beta 0 and covariance matrix sigma. So sigma is a p by p matrix. So you can assume that. So adding this layer, you are a Bayesian because this beta is a parameter and you assume it to be random. So this is what will give us the prior. And this will give us the likelihood. And you combine those two. So likelihood is about how the data is from, right? And here you, of course, you have I go from 1 to n for all of them, all the data together. So then once you do Bayesian, you are going to derive the distribution of beta given y1 to yn, given your data. And this will still, can be shown, is still a multivariate normal. And but now the mean and the covariance, so the first term will depend on beta 0 and x and the design matrix. Okay, so both will go into the first term for the posterior mean. And also for the second term, the prior covariance sigma and your noise variance sigma squared, they will both go into the second term for the posterior covariance matrix. So I'm not going to give the detail, but that's the essence of Bayesian linear model. So if you're a true Bayesian, then beta 0 and sigma should be known. Then beta 0, sigma must be known. So you actually have a prior. But if you don't, that's usually the case, right? We just use the Bayesian framework, but we don't really have a prior. Then these two things needs to be obtained in some way. So what empirical Bayes does is that you estimate them from data. Okay, have a distribution. So assume a parameter follows the distribution, but prior parameters are estimated from data. So this is what empirical means. So empirical is related to the use of data. If we learn the prior parameters from data, we are empirical Bayesian. Beta 0, sigma estimated from data. Okay, so if I ask you, how would you estimate beta 0 and sigma from data? What would you do? The most natural thing is to write down the marginal density of y, right? So the approach is like this. So you are going to consider these two layers of distribution as a hierarchical model. You see here is related to this hierarchical linear model in the H. So by treating it as a hierarchical model, So what you can do is you can write down the joint density. I'm just going to use the P to stand for probability density or probability mass function. So you are going to obtain the joint probability of y1 to yn. I'm just going to denote it by y. Okay. So data, I just give a notation y from y1 to yn. Transpose. So for this data, what I want is to derive its joint distribution just given beta 0 and phi. And this can be obtained from this fact that I first obtain the joint distribution of y given beta for any particular beta times the density of beta given beta 0 and the covariance matrix, and then I integrate out beta. This is the typical approach to remove the intermediate parameter. So with this integration, you are only left with these hyperparameters, beta 0 and sigma. And then you can consider this joint density. You can define, and we call this as the marginal distribution, okay? And given this marginal distribution, you are going to call this as the likelihood of beta 0 in covariance matrix, sigma. And then you can obtain, you can do MLE to maximize this. You know, this likelihood now involves your data, and the only two unknown arguments that can change is beta 0 and sigma. Then you do MLE to obtain beta 0 hat and sigma hat. And then finally, in your posterior, then go back to posterior. Then in posterior, which is beta given y, follows what distribution? You plug in your estimate for the prior parameters. So you are going to put beta 0 hat x into the first term, and you are going to put sigma hat, and of course, sigma squared needs to be estimated from your data in this Bayesian linear model. So put it here. So you are done. So in other words, this empirical base borrows the framework from Bayesian, but in fact, the prior parameters are also estimated from data. So you do not really have any prior knowledge, although you pretend to have. But what you have is just assuming this shape. You're assuming that the parameter follows the normal distribution, but you have no idea about the distribution parameters. So that's the general introduction to empirical base. And you can see that this is a very important thing to do if in the case, okay, so after, when is it useful? When should we consider empirical base? When is EB useful? Okay, so my take is that it is very useful when some parameters only have a small number of observations. Only have few observation to be estimated from. So in other words, you don't have many observations to support the estimation of one parameter. So to help you understand this, we will talk about the first and simplest type of linear mixed effect model. That is what we call random intercept model. Okay. So that will be the first model we will talk to start our discussion. And this is still the most common LMM or HLM in practice. So now let's take a look what it is. So by the name, you can tell there must be intercept. and the intercept is assumed to be random. So to start with, let's look at something we call a school effectiveness example to motivate this study, to motivate this model. School effectiveness data. So you can check the notes. This data is from 1996. And the data is regarding, here the response you're interested in are student standard test scores. Okay. Students test scores, such as the SAT score. And what we have is the school label. So the covariate is, actually we have two types of covariates, I should say. There are two covariates. The first one is the school name. Each student is from one school. And the second type is that we divide the school into two districts. So the school belongs to two districts. Each district has multiple schools. So the school district. And we can just label them as 0 or 1, just two districts. That's the question. That's the data, sorry. And the question is there difference in the two school districts? Or is there any difference between the two school districts? That's the question. So then how do we formulate this question? So of course, there are two types of approaches. So what we can do first is that we can just run a linear regression, right? So the first, how do we approach this question? Let me give you some extremes and then you can take a look. Okay, so the approach one is approach A. I guess this is probably some of you might use. So let me just give you some notations. So I'll say to the school names, I should say here we have 38 schools. Okay, so I'm going to denote this as, okay, 38. Okay, and this is a categorical variable. This is also a categorical variable. So we have two categorical variables or two factors here. So then the first approach, we can use the notation as Yij. Let me give you the notation. So let's say that is the score of student J in school I. That's the response. And of course, we have I go from 1 to 38, and J is nested in I, so we assume the size of school I is Ni. This is what we have been familiar with. And what's associated with it, the school district, we call it Xij. Okay, so it's actually, or I should say, it's just Xi. It's just Xi. For school I, we have this covariate Xi, which is binary, indicating which school district the student is in. Okay, so you see, we have a pretty clear scenario. So what do? The first case is that we just take this is our response, and this is our predictor or covariate into a linear model, right? So we could assume Yij is equal or follows, I just write down the random structure, is following a normal distribution, assuming the score is normally distributed, but this is subject to your opinion, but let's just put it simple. Assuming it's a normal distribution with the mean just depending on the school district, okay? So I can say that this depends on xi beta 1 plus beta 0. So I have a common intercept, and this is the additional intercept change related to the school district and sigma square. Okay, that's the approach one. And I can assume that this is IID for J and independent for I, for different school I. So I can assume this. So this is the approach one. Then you can see how would we estimate this beta 1 hat. So of course, you can always use that OLS formula to do the job, right? You can just decide what's the design matrix X, and then you can just do X transpose X inverse X transpose Y, and you're done. But we can show that with that approach, then basically beta I hat, this effect of school district would be equal to the average of the scores from schools in District 1 minus the average of the scores from schools in District 0. Okay, so I can just write this as the summation of, let me see, how many ones do I have? So this is just the number of school, let me see. Yeah, so I can just do this. It's I from 1 to N. Oh, I from 1 to 38. 38 schools I have here. And then I can just do Ni times the indicator that Xi equals 1. If the school is in District 1, I take that into account. And I'm calculating the total number of students in District 1. And then I take the sum of their schools and also the sum of students, Yij, if Xi is equal to 1. So I can do that. I can move this indicator outside of the sum, but that doesn't change the result. Minus 1 over summation, still I from 1 to 38, Ni times indicator Xi equals 0. And the second thing can be written down similarly. Xi equals 0. So I can do that. And I take the difference between the mean. That will be beta 1 hat. That's our first approach. So you see, in this approach, what we did ignore is what? The school difference. We just used the school label, right? We didn't actually use the school, or we only used the school district. We didn't use the school names at all. We are basically pulling students from school district 1 and from school district 0. And we didn't use the individual school information. Okay, so this one, pool all schools in one district. The reason is because here our beta 0 is a common intercept. Okay, so you may wonder, this is something problematic because the school should carry some information with itself, as students in one school may perform similarly, and there might be some differences between the schools within one district. So that gives us approach 2. So in approach 2, what you did is that you assume a specific school intercept. Okay, I write this as beta 0 I, like that, beta 0 I. Yeah. So xi beta 1 plus beta 0I sigma squared. So then you can see that we still have the in terms of randomness, it's still IID for J. For students in one school, they are IID. And we're still assuming the independence for schools I. But the thing is that here, the beta 0 here becomes beta 0I. So we have a lot more parameters to estimate. So previously here, we actually have the beta 0 common, so we can directly cancel them out in this approach, right? Because no matter which schools we are from, we always have the same beta 0. But here, beta 0I is associated with the ith school, and we must take that into account. So you can see an immediate effect is that we are going to have a lot more parameters to estimate. So previously, there's only 2 parameters, but now we have 1 parameter here and 37 parameter here actually, or 38, because we have we can think of it as either as 1 common intercept, 37 offset, or 38 intercepts. So either way, we have 38 here. So the number of parameters instantly go from p equals 2 to p equals 38 plus 1, 39. So we need to deal with that. So you probably wonder, okay, there might be too many parameters for me to estimate. And then coming back to, when I say the motivation. So when you have some parameters that only have a few observations to be estimated from, so you might assume, okay, yeah, I can use students in school I to estimate this beta 0I, but I will have maybe some school may only give me data for 3 or 4 students. Then that's what I mean. You have only 3 or 4 observations from which you could estimate this particular parameter. And that is not something ideal. Okay, so what is this? What does this actually mean? So probably I can give you a better illustration about what this means. So previously, when we say this beta 0 at the common intercept, you are assuming that, so for my, if I plot my data, okay, I plot Yij in the y-axis, if I draw here, so in scenario A, so if you plot your Yij in one x-axis and your xi in another axis, and this is 0, this is 1. So let's say your data are all pulled like this. Okay, then you draw a line as the linear regression line, and then you have a common beta 0. That's it. But here, it may be a little different. So you are actually, when you do this in approach B, you don't assume there is a common intercept. Instead, you are assuming that, okay, the intercept may change with schools. That actually complicates the issue, because let's say that still xi can be 0 or can be 1. But let's say you have some schools here, some schools here, some schools here, some schools here. So you need to take those into account. So essentially, when you fit this model, you are not fitting just one single line. You are doing multiple lines. But here the thing is a little bit trickier. I think the example here is a little trickier in the case that you do not have a school that belongs to both 0 and 1. So you just have a school either here or either here. So in other words, the intercept must be estimated from this school just in one condition. Okay, so that is a combination of both this effect of school district as well as the baseline of that school on its own. So yeah, so that's just the case. So you're not fitting one line at a time, but it's actually two. So for each school, although I know it's going to change, I know even though I assume they're change from one district to another district, I expect the same slope from xi from 0 to 1. But I expect that different schools may have their different baselines. So you can clearly see that there might be too many parameters in this approach B. Then the empirical Bayesian approach, or this is the general way of calling it, or more specifically, the random intercept model. I'll call this in short as RIM. In this case, is that we do not assume these beta 0i to be, or we still think of them as 38 parameters, but we are not interested in their values. So what we do is that we specifically added a layer for those beta 01 to beta 038. So what we do is a 2-layer thing, as we call it hierarchical linear model. Okay, so that's still here. But additionally, we assume beta 0i. For I go from 1 to 38. They are ID and they are scalar following a normal distribution with a mean parameter beta 0. We can consider this is the common intercept we assume like in model A. But now for each specific school, they are around this common intercept with some variance, and we call that as tau square. So with this, you see the number of parameters is effectively reduced for P. Okay, we ignore the sigma square always. The number of effective parameters is just beta 1, beta 0, and tau squares. So you just reduced the number of parameters from 38 for beta 01 to beta 38 to 2 in this prior. Okay, so probably to make it more exact, I can tell you P equals 2, P equals 38 plus 1. And that's not a good way to write it, but let me just say theta is beta 0, beta 1, sigma square. That's the parameters we have in approach A. And here in approach B, we have theta as beta 01 to beta 38, beta 1 sigma square. That's the case for approach B. And for approach C, here theta becomes beta 0 tau square, beta 1 sigma square. So you see, compared to approach B, we have a lot fewer parameters, right? And compared to approach A, we only added one additional parameter, that's tau square. So in other words, under approach 1, we are essentially assuming beta 0 to beta 01 to beta 038 are all equal. Okay, so let's compare those. So A, B, and C. Let's do a comparison for beta 01 to beta 038. So under A, the assumption is that they are all equal to beta 0. So they're all common, the same intercept. Under model B, we assume that they can all be different. So they can all vary freely. And under model C, we still can allow them to be different, but we add a constraint by requiring that they follow a distribution. So this is what we do in model C. So by adding this constraint, we introduce an additional parameter tau square to be known. Okay, so do we have any questions for this random intercept model? Yeah, there is a question popped up. Can someone just speak up? Is there a test to see if our normal assumption is valid? Yes, if you fit in which normal assumption? You mean the one for the prior?
Yes.
I don't think so. I don't think there's a way to check it, because essentially you see why. The reason is that when you draw data from, okay, in this model, when you draw data from this distribution, it's depending on one set of beta 01 to beta 038. So in other words, you only have one set of realization from the prior from which you draw the data. That means you don't have repeated measurements or repeated realizations of the parameters. So I would not say that is possible. And also, if you want to obtain some estimates of beta 01 to beta 038, you had to use approach B. But the issue with approach B is that you do not have many observations to support the estimation of each beta 0I, which means that the beta 0I hat you have as your estimator is very unstable. So you cannot really say my beta 0I hat is close to my beta 0I. So therefore, there's almost no way to really check this assumption, in my opinion.
Thank you.
Yeah, but that's the case with Bayesian. So if you're okay with Bayesian inference, then in a lot of Bayesian, the prior were assumed just by convenience, like when you use conjugate prior. Here's the case: this prior is conjugate with the likelihood, with density, data density, so that when you do the posterior, it is still normal, right? So like this case. So we have the conjugate prior for convenience. But yeah, that's definitely something people have been debated for over a century. So about which you prefer, Bayesian or frequentist. On each side, there is something to criticize about. But when we specify the prior, one thing to consider is the convenience, whether it's conjugate prior. Another consideration is whether you think it's a reasonable assumption. So for example, for each intercept, as we know that the intercept could be negative, could be positive, and it could be zero. So in that case, people think it's reasonable to assume that the intercept itself is just some fluctuation around the common intercept, and normal seems to be a reasonable assumption. Okay, so yeah, that's the random intercept model. And so then one thing I want to say about it is just something. I think I want to say this a little bit before we move on to the more general case. Okay, another example. Okay, so let's say this is example one. Example one. Okay, and the second example I want to talk about, there are more materials in the lecture notes, so I will suggest that you read them. And the reason I think that for this part, the notes seems to be a lot more scattered. The reason is that when I prepared for this lecture several years ago, this class, so for this HLM or LMM part, it's really not as organized as the GLM part. So a lot of textbooks talk about the same thing in different ways. And so you will see a lot of redundancy in the terminology and examples. So what I did is I tried to lay out as many examples as possible to give you some enough motivation so that you think, okay, this is reasonable. And as Evan asked, seems to be a sacrifice, right? You have to sacrifice some parameters for estimation so that you can estimate the parameters of your interest efficiently. And sorry, I forgot to say that the reason that we are not so interested in those 38 intercepts in our approach C is because we want to focus more on this beta 1. That is the effect of school district, and that's the question we are interested in. So, aside from the parameter of interest, the fewer other parameters we have, the more efficiently we can estimate this beta 1. So that gives us a lot of motivation to reduce the number of unnecessary parameters. And in statistics, some people call those other parameters as the auxiliary parameters, which means that they are not essential. They are just something that's out there, but you're not really interested in their values. Okay, so the second example is what we call the paired two sample t-test. What does it mean? So let's say that you have a clinical trial and you have n patients. Okay, and each has 2 measurements before and after treatment. Okay, so in this case, you see that your data points are clearly grouped into n groups. So we can denote those as, say, y10 to n0. So these are the before treatment observations. And we have for each patient the after treatment observation, y11 to yn1. This is the after treatment observation. And we want to compare these two to see whether there's any treatment effect. So for example, this could be like a treatment of diabetes, and we can have the weights of the n patients before treatment and their weights after the treatment. We want to see whether there's any reduction in their weights. That's the setup. So we know how to do it, right? If you have ever learned a pair to sample t-test, we are going to take the difference for each patient, and then we will test whether the mean of those differences is 0. So we're going to test, say, let me see. So let's say we just take zi as the difference of y I1 minus y I0. We do this, and then our null hypothesis would be whether the expectation of zi is equal to 0 for all the i's. Okay, so that's what we want to test about. But here the key thing to bear in mind is that if you think of this as a linear model, then you can always think of it as our setting. Okay, so from a linear model perspective, we can think of as yi j, okay, following a normal distribution with an intercept beta 0I. So each individual has a baseline weight plus the effectiveness of treatment. So we can say that is beta 1 times the indicator that j is equal to 1. So because j is the jth observation of the individual I and the common error term, so here j goes from 0 to 1. So that just indicates the treatment. And whenever you have a treatment, you add this beta 1. And of course, you have this varying intercept for individual I. So you see, this is another example where we are essentially considering the intercept to be different for different groups. And so basically here the question becomes to test whether beta 1 is 0 or not. That's our parameter of interest because that reflects the effect of treatment. And so for this single example, you see the way we do it is that we basically take the difference between yi1 and yi0. So effectively, we assume that, okay, once we do that, their expectation is just equal to beta 1. So each zi's expectation is equal to beta 1. So then the null hypothesis becomes whether beta 1 is equal to 0. But because this problem is so simple, we can just do the subtraction to get rid of these parameters. So we are left with estimating beta 1 only. So that's just the simple thing about this setup. But still, you can see the same flavor out there. Okay, do we have any questions about the existence of groups in our data. So the take-home message, let me just give you a simple take-home message. So the take-home message is that you may consider this random intercept model if there are many small groups in your observations. So like in the first example, we have 38 schools that can group the students. In the second example, we have n groups. So each group corresponds to one patient. And within each group, the number of observations is very small. Okay, do we have any questions? Okay, great. So now let's move on to our more general perspective for linear mixed effect models. More generally, okay, so what is our hierarchical linear model? Let me just give you the simple setup. So what we can do is to say that we divide, or maybe I'll say hierarchical linear model or LMM. I'll talk about them together. So the first layer, let me change to a different paper. The first layer is about what we are familiar with. But we need to divide our covariates into two types. Covariates into two types. Okay, the first type of covariates is the ones whose effects on the response are of our interest. So using our previous examples, for example, the school district, the treatment, these two are covariates of this type. We really want to investigate their effects. And the second type of covariates have effects on the response as well. Just as the school, like one of the 38 schools, what school the student is in clearly has an effect on his or her grades. So on the response, but are not of interest. Covariates that have effects on the response that are not of interest. So some covariates including the school names, the school themselves, and the patients. So in the second pair t-test example, you can see we are not really interested whether what the effect patient, okay, like the average weight of patient I before and after treatment, right? So we're not interested in the baseline of patient I, although that is affecting the measurements of patient I, but it's not of our interest. So in those cases, after we decide, okay, our covariates belong to these two types, the first type of covariance effect will be called fixed effect. And we are going to estimate them, to be estimated. And the second type of effects are there, and there are many, but they are not of our interest, so we assume them to be random effects. And we are not going to estimate them individually, but their prior parameters are to be estimated. Okay, whose prior parameters to be estimated. Okay, so that can essentially reduce the number of parameters we will estimate. I think this is a very smart way of thinking of the problem. So we are being realistic, and also we are not being stupid, right? Being realistic means that we do not have too many parameters to afford, but we're not being too stupid by estimating too many parameters that are not of our interest. So empirical base satisfies this perfectly. Okay, so now let me write down this LMM. Okay, so the first layer is just we have yi. So still, let me use the school example. School I. Okay, so I from 1 to n. And I call the observations nested under school I, or maybe you can make it, I can make this more general, group I, not call it school. So group can be a school or group can be a patient. You can think of this way. So I will call yi1 to yini. So all the observations, all the responses in group I as a vector. Okay, that's my notation. And then the covariance of type 1. I put their design matrix, I call it xi. And that means I have, so these are the covariates corresponding to this person, this observation. I call that xi1 transpose to xi transpose. Okay, so then the dimension of this part of design matrix is ni by p. That's covariance 1. And for the second type of covariates, I put them into another design matrix I call zi. So zi indicates the design matrix of the random effect. And I call them zi1 transpose to zini transpose. And I also give their dimension. So just for simplicity, and this is a common term or common notation used in the literature, we call that there are R random effects. So for example, let me give you some intuition about this. So in our previous school example, we are going to have 2 columns in the covariate design. Okay, sorry. We are going to, in the school example, go back to this. So in these 2 examples, xi will just be 1 column. So that just contains the covariate of interest, like the school district, like the treatment. And here the R is equal to 1. So it's just the intercept. Okay. Yep. R is just in the intercept. So this is what we have under the random intercept model. We put the intercept as a random effect here, and we put the school district or the treatment as the covariate of our interest here. So P is 1, R is 1. I hope this can connect that with you better. Okay, so that's it. And then the model is assumed to be model of group I is assumed to be this using our vector notation, yi equals x times beta. Beta is a p by 1 coefficient vector plus z times gamma. Gamma is an r by 1 coefficient vector plus xi, my bad, zi. Okay, please note that this beta, here's the key thing. Beta is not within group I, because beta is just a common effect we are interested in. So for example, here is the treatment effect or the school district effect. This has nothing to do with our group I. But this gamma, we need to put an I here because this gamma I is the effect within group I. And it is the thing we're assumed to be random. So like here, Gamma I is the intercept of group I in our random intercept model. So that's why gamma needs to carry I with it, because it's a group specific effect. So let's say that beta is a common, not group specific effect, while gamma I is a group specific effect. Because our I can go from 1 to n. So if n is large, that means we have many groups. So gamma I may be many. We have many gamma i's. So that's why for practicality, we assume they're random. And beta, this is something of our interest. We assume it to be fixed. And that's our hypothesis testing about. Okay, and of course, we still need a random measurement error term. So that will be our epsilon I. This is an ni by 1 vector. So that's the model. And if we write them together in this way, this is what we call linear mixed effect model. The mixed effect stands for, we have fixed effect here, we have random effect here. Yeah, so together they are mixed effect. So if you think from the randomness perspective, the only term here that is fixed is this part, the covariate of our interest and its effect. While these latter two terms, they are both considered to be random. Okay, does that make sense? Okay, and then we also need to have some assumption, right, on the epsilon I and on this, okay, sorry, I think I'll call that sigma I. I'm not using a consistent notations with my notes. Let me check. So yeah, I think this will be better. So I'll call that delta I. Sorry, this will be delta I. So then what we need to assume is that this is just laying down the model, but the random distribution or how the randomness of delta I and epsilon I hasn't been specified yet. So in linear mixed effect model, what we assume is that this epsilon I and delta I, they are going to be jointly following a normal distribution. What will be the dimension of that distribution? Epsilon I has ni dimensions, delta I has r dimensions. So this should be ni plus r dimensions normal, okay? And we are just assuming that this is just having a 0 mean. Okay, so one thing here. So now you see there's something tricky here. If you want to use this setup and assuming, okay, this random intercept has mean 0, you need to do something different from before. Remember, in our RIM, here, let me see. We have the random intercept following a mean of beta 0. And this beta 0 is the common intercept just as in model 1, model A. And this common intercept may not be equal to 0. Okay, so if you want to do that, what should you do? You actually need to be consistent with what we said in this setup. If you want to assume the random effects all have mean 0, then you need to move that common intercept back into the fixed effect. Okay, this is something I need to pay attention to. So that you have an intercept here, and you also have a random deviation from the common intercept. And that random part is considered to be mean 0. So sorry for confusing you previously, but now I realized that I need to put the intercept back into the fixed design matrix. So basically, you will have an intercept here that corresponds to column of ones, but considering that different groups may have different intercepts that deviate from the common intercept, so then you assume that the random part of the intercept has mean 0. Does that make sense? Okay. So, and also if you have some coefficients, like I said, so in our previous example, we assume the school district effect is not related to the school name. In other words, we do not think, okay, for the district, it has different effects on different schools in that district. For example, in a realistic scenario, the school district may actually have some effect on the school. For example, if you have a good district and a bad district, then probably for schools on the boundary, geological boundary, they are less distinguishable from each other. That's possible. So that's why in this case, if you want to assume that your district effect, let me go back here. If you want to assume this beta 1 is also depending on school I, then you will have beta 1i here instead of beta 1. So that means we have random coefficient model, not just random intercept model, but the coefficients are also different. So if that's the case, then you are going to have the common beta 1 in your design matrix. So you are going to have the school district here, but you may also add that column to Z as well, so that you can allow that different schools have their coefficients also with some deviation from the common effect. So that can actually make your ZI with one more column and also make your delta I with one more parameter. So these are all possible. So as I can say, so in the full linear mixed effect model, what you can do, in fact, is that you could actually have everything here, also here. So you can have the design matrix with the same dimensions. That's possible. So in this case, you are allowing every fixed effect to have a random companion. And that random companion, it reflects the group difference from that fixed effect. But we're not going into that complexity in general. And I would say the random intercept model is the most common one in practice. You just want to assume different groups have different intercepts and no more than that. Okay, so I've said enough. And then for this random part, so we assume that they have mean 0. And also for simplicity, we assume that there's no dependence between epsilon I and delta I. So we assume they're independent. So we have off diagonal 0. And for epsilon I, which is the error, measurement error terms, we assume that they have this. So they are following a covariance matrix with index I, okay? And for this delta I, it's the random effect. So of course, we want to assume that delta I is the group I's effect, and across all groups, their random effects following the same prior. So we assume that they have the common covariance matrix. So you see, this is a way to write it. Or you can write it in this way. If you are more familiar with that, that is epsilon I following normal distribution with ni degrees of freedom, mean vector 0, and covariance matrix sigma I. And we have delta I following normal distribution with r degrees of freedom, mean 0, and the common covariance omega. And then these two random vectors are independent of each other. So this independence is very important because then we can allocate the variance in our response into the variance in the random effect and the variance in the random error. If they are not independent, then there's overlap. That will complicate this case a lot. And we don't know how to talk about their dependence. So that's why for convenience, we assume independence. And that's something we must do so that the model is actually identifiable. Okay, so this is the general setup, but usually we may actually make the sigma I even more simpler as we did in our linear model. So usually we just set sigma I to be a diagonal matrix with sigma I squared in the diagonal. Okay, so this means that within group I, our random measurement errors are independent. They are all independent, and they have the same variance sigma I squared. Okay, you may do that, and you may even simplify this. So for example, since if I don't have many observations in group I cannot estimate delta I well, right? So that's the reason we want to assume delta I follows a common prior. So we don't need to estimate individual delta I, but we just need to estimate omega. That's the motivation of this whole story. So if you cannot afford to estimate delta I well, then it is likely you cannot estimate the sigma I squared well, right? So that's why if you don't have really many data points in your group I, then even simpler, you may assume that sigma i's are all equal to a common sigma square for all the i's, I from 1 to m. So in other words, across all groups, you can assume their random measurement errors all share the same variance. And then you are going to change this sigma. Then all the sigma I here just become sigma squared diagonal, right? And this is ni by ni. So I would say this is the most common case. We assume a common variance for all the random measurement errors. Okay, but we haven't talked about this omega yet. So omega is just in the prior of this delta I. And often we also need to simplify that. We usually do not assume this to be an R by R covariance matrix. So depending on how large R is. So in our random intercept model, R is 1. So this omega was the tau square we talked before. But it depends how many R we have. Okay, so that's all for today, and we will continue on next Tuesday.